Yeah, camps on everyone. Let's start off. There, this was the last thing that we did. Let's see one more like this before going ahead. So we have two springs connected to a block like this, initially at rest. Now you cut one of the spring. Find the acceleration of the block when the spring is cut. Other scans on. Let's get this. Any answers? You know how springs behave. So when you cut one of the spring, the other spring doesn't care. It'll still exert the same force which it was exerting before the cutting. So first find the tensions in the springs. So this will be the spring force Kx. Kx. This will be theta. Kx cos theta, Kx sin theta. And initially it was mg. So 2Kx sin theta is equal to mg. This was the initial force. Now when you cut one of the spring, So the right spring is gone. So the left spring will continue to exert the same force. And there is an mg. Now remember, this won't go in a circle because the spring can stretch also and it can move also. So now take the forces. This will be kx cos theta and this will be kx sin theta. And kx sin theta is nothing but mg by 2. So this block will have acceleration in two directions. It will have a vertical direction. It will have an horizontal acceleration. So kx cos theta will be mass into acceleration. So ax will be, kx is how much? mg by g by 2 cot theta. So take kx from here and substitute. And in the vertical direction, it is kx sin theta minus mg is equal to may. Ay is g by 2. There, that's your acceleration. So acceleration of the block will be minus g by 2 cot theta I cap minus g by 2 j cap at this instant. Next moment theta will change, block will move, x will change, a lot of things will happen. So this block not only goes down, it also goes to the left. Have a look at the steps. So this is the difference between a string and a spring. If you see the last question that we did, in case of a string, the string could not stretch in this direction because the length of the string is constant, but length of the spring need not be constant. So if you actually try to see this motion, it would look something of this sort. This thing is coming down also and swinging also. So this is not a circle, this is something else. Do have a look at the steps. This is before cutting and that's after cutting. Clear with this? Next thing. Pseudo force. Now, most of the problems in loss of motion, right? You can do them without any pseudo force. I would not suggest also to use pseudo force maximum time because it takes away the understanding and all. Yeah, sometimes it is convenient, but maximum problems you can do without pseudo force. It is convenient in few cases, but especially in circular motion, we're going to use this a lot. But so we will just have a little introduction about it. We'll see a few problems on this. And I'll show you a few cases where you can do it in the ground frame also with pseudo force also. It really won't matter much. So what is this pseudo force? Now, in certain cases, it is convenient to solve with respect to a non-inertial frame, just like relative motion. What is a non-inertial frame? Any frame that accelerates with respect to the inertial frame. So accelerating frames are non-inertial frames. So in non-inertial frame, loss of motion, they don't work, they fail. I'll show you examples. So your loss of motion, the first law, second law, and all this, they don't work in non-inertial frames. You start getting actually all errors. But still, you insist like, I want to do in the non-inertial frame because sometimes it's convenient. Then we have to introduce some kind of a correctional factor. We introduce a correctional term. So this is a mathematical correction, okay? Pseudo force. Look at the word pseudo means false. Force. So it doesn't exist. It is just a mathematical correction we have introduced in order to make our equations right. So we introduce a correctional factor called pseudo force. in order to use the loss of motion. So what is the pseudo force given by? So the definition of pseudo force is it is mass of the body being observed. So whichever body or whichever is your system that you're observing, you take the mass of that body into negative of acceleration of the observer. So whoever is observing this block, uska acceleration of the observer. So mass of the body you're observing and negative of the acceleration of the observer. Let me show you how this works. So this is the formula for pseudo force. And you will see how we got this also. So example, let's say we have an observer who is going with acceleration a1. We have a block here m which is going with a2. Now if you ask this person, boss, what is the pseudo force? Pseudo force on m as seen by the man. Again, what is the formula? Mass of the body, which is m, into acceleration of the observer, which is a1 minus a1 I cap. So the pseudo force is given by m a1 I cap. And if you notice something, this is independent of a2. Pseudo force doesn't care what is the acceleration of the object. Pseudo force depends on the acceleration of the observer and mass of the body. So let this block go with any acceleration it wants. The pseudo force doesn't care. Pseudo force simply depends on the observer. So that is how you calculate the value. Let me show you how to use this. But have a look at this. And you'll see why you're getting that m into minus sign and all that. So we have actually taken the Newton's second law and we have just arranged the terms. So let's see an example. Let's take a scenario. Let's say we have a lift. Inside the lift, you have a spring balance attached to a block. And we have seen last time, a spring balance gives you the reading tension in the string by G. Now let's say we have two observers. We have observer A on the ground who is at rest. We have another observer B inside the lift. And let this lift go up with acceleration A. So the lift is a non-inertial frame. It is accelerating. Now, if you ask both of them to draw the FBD, this is what A will say. Now remember, forget about inertial frame and everything. If you just ask A, boss, draw your FBD and write the forces, he will say, okay, I see a block M. There is a tension T. There is an mg. Since the block is inside the lift, it is also accelerating with A. Then Newton's second law equation, net force T minus mg. Remember, these are the forces. A is not a force, A is an acceleration, the effect of this. That is equal to mass into acceleration. So he will say tension in the string is mg plus ma. And when he actually checks the spring balance, he observes you get the same answer. The spring balance also shows mg plus ma. So there is no problem. This is what we have been doing so far. Now, but if you ask person B to draw the FBD, B will say, okay, he will say, okay, there is a block M, there is a tension T, and there is an mg here. And I think the block is not moving because he is at rest, he's inside the compartment. So he will say the block is not moving because both are inside the compartment. He thinks it is at rest. So B thinks block is at rest. So he will draw the FBD according to him. And then he will write T minus mg is equal to 0. So he will get tension is equal to mg, and which we know this is wrong. So when he's calculating on a paper, he will get T is equal to mg, but when he goes and sees the spring balance, he will see something else. That is how you know you're an accelerating frame. Your equations and your experimental readings don't match. So B will understand there is something wrong. My equation says net force is ma and A is 0 because I'm inside the compartment. I think the block is not moving. So B will realize, boss, there is some problem here, right? So now B will say, okay, there's an acceleration. So if you want to do this correction now, but if you insist I want to do with B, so we have to include a pseudo force. So we tell B, boss, you're in a accelerating frame. So in your frame, the laws won't be valid. So then B, if he uses with pseudo force, this is what we will say. There is a tension T, there is an mg. Since I'm in an accelerating frame, so who is the observer here? The left is standing there B. Is actually going with acceleration A upward. So the pseudo force is mass of the block and acceleration of the observer in the reverse direction. So it should be kept down. This is your pseudo force. For all equation and mathematical purposes, we can use this, but technically it never exists. And if you ask him what is the acceleration, understand he will still say acceleration is 0. He will still say acceleration is 0. He will not think the block is moving. But now when he writes the equations, tension minus mg minus ma net force is equal to mass into acceleration, which is 0. Just because you use pseudo force doesn't mean he will think the block is moving. It is still at rest. Now he gets the equation T is equal to mg plus ma, which is right. Suddenly the equations start becoming right. Are you clear with this? So indirectly, what we did? T minus mg is equal to ma. We took this ma ka term and we shifted it on the left hand side and we started calling it pseudo force. Isn't that what we're doing mathematically? That was the reason the pseudo force came out to be mass into negative of acceleration. The reason you're getting a negative sign is because you're shifting it from the RHS side to the LHS side. And that's not a force cut term, that is an acceleration cut term. So you created a mathematical term called pseudo force and you're introducing it to make your equations right. So the pseudo force doesn't exist. Are the steps clear, everyone? All clear with this, how to use pseudo force? So how to use pseudo force? First, ask yourself, who is my observer? Before directly randomly putting a pseudo force, the first question you should always ask is, who is my observer? If you say A is my observer, don't talk about pseudo force. If you say B is my observer, then talk about pseudo force. So one of the most confusing thing that I see, right? People don't understand, like, should I put pseudo force? Should I not put pseudo force? The question is wrong. The first question you should ask is, who is my observer? If you tell me who is the observer, then accordingly, I can tell you how to do that. Let's take one more example. Let's say the same thing, we have a vehicle. This time the vehicle is accelerating horizontally. And let's say inside this, we have a pendulum. So if you leave a pendulum like this, you will observe the pendulum will actually make an angle theta. Right? So let's say the question is find theta. Gravity is present as usual. Again, let's take two observers. Let's say if A is standing outside and let's say B is standing inside the compartment. Now if you ask these two people to solve, so if you ask A to solve, this is what A will say. How many forces are there on the pendulum? Tension T, string, and mg. That's it. He will say there are only two forces. Since the pendulum is inside the car, it will also go horizontally with acceleration A. Then resolve the forces. So this is also theta. This will be T cos theta. This will be t sine theta. Vertically, there is no acceleration. So t cos theta minus mg is 0. So we get tension is equal to mg by cos theta. And horizontal direction, t sine theta is the reason the thing is accelerating horizontally. Take t here and substitute. You end up with mg sine theta by cos theta is equal to ma. We get a is equal to g tan theta. Same question if you ask B to solve. Are the steps clear, everyone? The idea is important, not in this chapter, because this, what I'm teaching you now, we're going to see this in circular motion again. There we will call it centrifugal force. Ever heard the term? That's actually a pseudo force. So we are going to use that extensively in circular motion. In this chapter, we will use it a little less. We'll maximum, most of the times I skip, except few cases where it is convenient. We'll see. So if you ask B to solve the same problem, B will say, okay, I'm in a box which is accelerating, so I'm a non-inertial frame. That's your first question you should always ask. Where is my observer? Is he accelerating? Is he on the ground frame? If you're standing on the, we take normally Earth as a reference frame. So if you're standing on the Earth, then you're an inertial frame. So he will say, okay, I have to use pseudo force tension, mg. What is the pseudo force? Mass of the pendulum, acceleration of the truck in the opposite direction. So he will put it in the opposite direction. This is your pseudo force. And if you ask him, what is the acceleration? He will say, what are you talking about? It is not moving. It is at rest. If you are inside the truck with the pendulum, he will think it is at rest. So now when you resolve the forces, if you think about it, you actually get the same equations. T cos theta and T sin theta. And this guy will write T cos theta minus mg is equal to 0. T sin theta minus ma is equal to 0. There is no acceleration. So basically you took that ma term on the RHS side and brought it to the left hand side and you started calling it pseudo force. T cos theta is equal to mg. Divide them. You get a is equal to g tan theta. Is this clear, everyone? Any doubts on this? So there. So before directly dumping pseudo force in the equation, ask yourself, who is my observer? If you can't answer that question, then I think you can't go ahead. If you say ground frame, don't talk about pseudo force. If you say accelerating frame, then it is fine. Then use a pseudo force. All clear with this? Let's see one or two models on this. So pseudo force is a mathematical term we have introduced for our convenience. It doesn't exist. Think of like this. When you're sitting in the bus, when the bus suddenly accelerates, you hit the back. Observe that. You suddenly go back when you're sitting in a car or a bus. In reality, what happened? You're sitting at the same place. The bus came from the back and hit you. But you think you have gone back. In reality, that's what happens. So let's say we have an accelerator here. Let's say this is going with A is equal to G by 2. We have a spring balance here. And we have an Atwood machine here. Let's say 3 kg and 2 kg. Find the reading of the spring balance. And acceleration of the blocks in the ground frame. If nothing is mentioned, it is always in the ground frame. 3.6 kgs, okay. What about the acceleration also? There are two blocks, Reshman. They won't have same acceleration. Ground frame में पूछ रहा था. Try. I'll give you a minute more. Hmm, 2.6. Okay, let's see. So we can actually do this a little faster if you think about G effective. So let me teach you the concept of G effective. So whenever you have any compartment or any system moving up with acceleration A, and if you take any body here, so what will be the forces on this? So if you ask the person inside, if you ask this guy what is happening, he will say the block will have force mg, its own weight, and it will also experience a pseudo force ma. So he will say, so this thing behaves as if the block has a total weight mg plus ma. This is your net force. But since we are so used to using gravity every time, I prefer to use a gravitational term. I will call this thing G effective. Quite a useful thing. Do remember this. We are going to use this a lot in other chapters. So G effective is G minus A, G plus A. So this person will think in that compartment, the gravity has become G plus A. That is how he will feel. So once you got this, literally you can play with everything. So in the box, if someone throws a particle, so the box is going up with A, and someone projects a particle with U and theta, and they ask you where is the particle landing, you can just replace everything with G effective. This will be your range inside of the box. So time of flight will be 2u sine theta by G effective. So wherever there is G, replace with G effective. Range will be u square sine 2 theta by G effective. So wherever there is G, you can replace that and finish it off. Same thing, if the box is coming down, then the person inside will think gravity has become G minus A because the pseudo force will be up now. And we will see in something more interesting things. Suppose if the box is going horizontally, this person inside, right, will actually stand like this. He will think this is down. So the pseudo force will be Ma, the gravity is mg. So in his world, the G effective will be this way. Since both are perpendicular, it will be root over a square plus g square. These things happen, where? Think of like this. If you take a compartment with water, and let's say compartment is at rest. If you accelerate this with A, you'll observe the water will actually become like this. So if you accelerate the compartment, the water actually makes an angle because the water will think the gravity has become this way. We will talk about that in fluid mechanics in more detail, but G effective need not be always up and down. It can make even angles also. This was the same reason in the pendulum experiment. See, because the pseudo force Ma was this thing and mg was this, the pendulum thought this was gravity. That's why the pendulum is making an angle theta. Is the concept of G effective clear, everyone? So the lift is going up, the person will inside the box will think G plus A. Lift is going down, G minus A. Lift is going horizontally, he will think gravity is becoming at an angle, which is root over A square plus G square. So in this box, if you keep water and if you accelerate horizontally, the water will actually make an angle. Is this concept clear, everyone? G effective. Any doubts on this? Effective gravity. Because Emacs doesn't care whether it is G or A. For Max, simply it is just a number. Now coming to this question. So if you keep the person inside the frame and if you ask him, boss, what is your acceleration? He will say, G effective is G plus A, which is 3G by 2. He will think the gravity has become 3G by 2. Now this has become simply an Atwood machine. This is 3 kg, 2 kg. But remember, all your answers will come with respect to the lift. So gravity is 3G by 2. This is tension T, this is tension T. So this tension will be 2T. We know tension ka formula in Atwood machine is 2 m1 m2 by m1 plus m2g. You can derive it, but if you know the result also, it is great. G becomes G effective. So everywhere it will be G effective. 2 into 3 into 2 by 3 plus 2 into 3G by 2. How much is this? 2 goes off. That is 326 by 5, 18 by 5. G. This is your tension. But remember one thing, the spring doesn't care what is G effective. The spring ka thing is designed to always show you T by G. So the reading of the spring balance is tension by normal gravity, not G effective. Because when you design the spring, inside the spring and inside the machine, everything, you thought you're going to use it on Earth. So this thing comes out to be 18 by 5 kgs, which is 3.6 kgs. So the spring balance will show a reading of 3.6. Wait, sorry, it will show 2T actually. Because the spring balance tension is 2T. That would be 7.2 kgs. It's not 3.6. Clear with this? Right, Utsa. Any doubts on this part? Because this thing is connected to the 2T tension. Anyone confused with G effective? Anything that you're not clear or convinced, please ask. Clear. We still have to find acceleration though. So once you got G effective, acceleration will be, this will go up. This will come down. So you know your formula for acceleration? M2 minus M1, that is 3 minus 2 by 3 plus 2 into G effective. That's 1 by 5. So 30 by 2. 3 meter per second square. Now be careful. This is the accelerations with respect to the lift. So acceleration of 2 kg with respect to the escalator or the lift is 3 meter per second square upward. Acceleration of 3 kg with respect to the lift is minus 3 meters per second square j cap. But you're asking in the ground frame. You know the formula. Acceleration of the block with respect to the ground is acceleration of the block with respect to the lift plus acceleration of the lift with respect to the ground. You just need to add the lift acceleration to this. So acceleration of the 2 kg with respect to the ground will be, lift is going up with 5 meter per second square. So just add plus 5 to both of them. This guy becomes 8 j cap. Acceleration of 3 kg with respect to ground 5 minus 3 will become 2j cap. So both the blocks are actually going up in the ground frame. So the person in the lift will think one is going up and down, but the person on the ground will think both are going up. Check. Hmm. So you just stand inside the lift, solve everything, get your answers in terms of the lift car frame. Come back to the ground frame and add your lift car accelerations. You will get in the ground frame. Is this clear, everyone? How to use this pseudo force ka thing? This problem, right, is very convenient if you do in the lift car frame. If you try to do this in the ground car frame, I'll just show you how it looks. It gets actually messed up. So if you stand here and do the problem, the issue is this will be tension T, this will be tension T, this is 30, this is 20, this will be acceleration A1, this will be acceleration A2. Both the blocks won't have same acceleration. And this part itself is going with G by 2. So we have to use constraints here. We will write 2T into G by 2 minus plus T into A2 plus T into A1 is equal to 0. We have to write a constant equation. Then write force equations. Then solve. You'll get the answer. But it becomes confusing and little lengthy. But the moment you stand inside the lift, it becomes a simple Atwood machine whose results you already know. So I can just replace everything with G effective and finish it off. So it's more of a convenience, saves time. Clear with this? So like I said, pseudo force will not really do too many things. But this is the main idea there. So especially when they ask you projectile inside a box, use G effective. Atwood machines in a box, something like this, G effective is useful. Let's see one more. So let's say we have a block here, small m. We have a wedge, mass m, angle theta. All surfaces are smooth. The ground is also smooth. This is also smooth. You release it from rest. Find acceleration of the wedge and the acceleration of the block. Till now, the wedge used to be fixed. Now the wedge also will start moving. You can do this in the ground frame. You can do this in the non-inertial frame. Doesn't matter. Let's try to do with pseudo force and see. Let's get this. It's a good one. Find the acceleration of the block and the wedge. In every equation, if they don't mention anything, they simply ask acceleration. They're asking in the ground frame. Try. Everyone should give it a try. How do we start this? So in this kind of problems, right, the first headache that I'm seeing is I don't know how that small m is moving. Normally, what used to happen, the wedge used to be fixed, and I was pretty sure the block was sliding along the incline. Now, unfortunately, it is sliding down the incline, and the wedge is also moving at the same time. So that is actually messing up. So let's see. So we have to start with something. So let the wedge go backward with an acceleration a1. So let the wedge ka acceleration be a1. And let's keep my observer on the wedge. So let's ask him to solve the problem. Right? So he is my observer, at least for the block. So he will think the block is coming down with an acceleration a2. So this a2 is an acceleration with respect to the observer. Because this I know, right? If I go and stand on the wedge, I know the block will slide along the wedge. This is the acceleration with respect to the wedge or the observer. Is that clear, everyone? Technically speaking, the block is coming down and the block is also going horizontal. It is going like this. There are two accelerations for the block. And it becomes confusing. So we need to get those two. Great. Now, step one, draw the FBD. What are the forces? Normal reaction, your own weight mg, normal reaction on the ground. That's it. There are only three forces acting on this, and this is my acceleration a1. I'm writing this in the ground frame. So for the wedge, we are writing in the ground frame. Because wedge is moving horizontally, that I'm pretty sure. But when I draw for the block, this we're writing with respect to wedge. Now, what are the forces? Mg sine theta, mg cos theta, normal reaction. Since the observer is accelerating to the left side, now we will get a pseudo force, which is m into the mass of the block into acceleration of the wedge. This is the pseudo force. Because the observer is standing on the wedge, he will think, yeah, I'm a non-inertial frame, so I need to apply a pseudo force, right? And what is the acceleration? The acceleration of the block is a2. So this guy also thinks there's an acceleration. And remember, I'm writing forces on the body, accelerations outside the body. There, we got the FBDs. Now let's write the equations. So if this is n, resolve this into components. This is theta. This is 90 minus theta. So this is theta. So this is n cos theta, which is pushing down, and this is n sin theta, which is pushing horizontally. Perfect. So for the wedge, we have n sin theta is equal to mass into acceleration, which is a1. That is your equation one for the wedge. For the small block, now I need to divide even this into components. Let me just redraw this again. This is mg sin theta. Now this MA thing also will have a component. So pseudo force ka component will be MA1 cos theta, right? Because if that is theta, with the incline, this angle also will be theta. So that will be MA1 cos theta. And this will be MA1 sin theta. This is your mg cos theta. Normal reaction is not mg cos theta, everyone. And this is a normal reaction. And this is your acceleration. Please check the components. Now write the equations. I'm choosing incline as x-axis and y-axis. So along the incline, if you see the forces mg sine theta plus ma1 cos theta will be mass into acceleration a2. What is the normal reaction? Normal reaction is mg cos theta minus ma1 sine theta. It's messed up. There are too many things. This is equation 3 and equation 2. Please check your equations. N is not mg cos theta. Because the wedge is also moving, that n now n minus mg cos theta, there will be an acceleration in that direction. So there you can see. So n is actually mg cos theta minus ma1 sine theta. How many variables are there? N, a1, a2. How many equations are there? 3. So we should be able to solve this. But first of all, before jumping into solving, please check the FBDs and check the equations. If you got this, then it is only max. Anything that you're not convinced, how did you take the force? How did you take the component? Why did I write like that? Anything that you're not convinced, please ask. You can confuse, please ask, unmute and ask. If you're feeling shy, please type in the chat box to the co-host, but ask, get it cleared. I hope the equations are clear. Then I think let's go ahead. Great, I have 3 equations. Let's start solving them. So n sine theta is ma1. Be careful, there's a capital M and small m. The second was n mg sine theta plus ma1 cos theta was ma2. N was mg cos theta minus ma1 sine theta. Perfect. So I want to find a1 and a2. I don't want n. So take this n, dump it in that equation. And yeah, perfect. Actually, I got a1 directly. Take it and dump it there. ma1 by sine theta is equal to mg cos theta minus ma1 sine theta. Bring all sine theta 8 ones together. mb sine theta plus m sine theta is mg cos theta. Therefore, a1 will be mg sine theta cos theta by m plus small m sine square theta. There, that's your a1. Once you got a1, put it in equation 2. So a2 will be nothing but g sine theta minus a1 cos theta. You can substitute there and simplify. I will leave it to you. You'll get the answer from there. Is this clear, everyone? So once you got the equations, it's just a matter of solving. So write the forces, resolve them in the horizontal vertical direction, write the equations and solve. Clear with this? Great. Next thing. Yeah, so that is a little about loss of motion. That would be the last problem for the chapter. So do make sure to go through the notes. We have done 54 problems, almost 200 pages there. So do check it out. We did different varieties there. Like I said, maximum, if you can, try to avoid the pseudo force ka thing. It's fine. If you're comfortable, use it. I generally don't prefer. But in circular motion, we're going to use it extensively. So there, it's better. Like I said, there are few selective problems where I saw it is pretty useful. Problem that I noticed, right? Randomly, if you try to use pseudo force everywhere, you start getting confused. Should I use? Should I not use? So I think that's a question you need to ask yourself before starting a problem. Where is my observer? So whenever you get confused about a pseudo force, ask yourself the first question. Where is my observer? You say ground frame, don't talk about pseudo force. You say observer is an accelerating frame, talk about pseudo force. Done. Then go ahead with how to solve. That's it. Once you put the pseudo force, it's a regular problem. Write the forces, resolve the forces, apply FBD, constant equation, solve. Clear this? Next thing, friction. Friction is, again, looks like NLM with only one additional part. Like I told you last time, whenever I see NLM and friction, I think of like this. Like NLM is like your plain dosa. Friction is like your masala dosa. It is still a dosa only. You just put more fillings, right? So if I had to explain the whole chapter in one or two sentences, this is the whole chapter about. If I say there is a block M, and if I say there is only one force acting on the block, if there's only one force acting on the block, and you want to find the acceleration, see Harry, focus on this. You can ask later on, right? So if there is one block and if there is only one force acting on the block, now you tell me what details you need regarding the force to get the acceleration. There is only one force acting on the block. What details you need regarding the force to find the acceleration? One is the magnitude, one is the direction, isn't it? If I know the magnitude and the direction of the force, then I can find the acceleration of the force, acceleration of the block, isn't it? That's it. This whole chapter teaches you only one thing: how to find the direction of friction, how to find the magnitude of friction. Once I know this, put it in an FBD, resolve the forces, write the constant equation, write F is equal to ma, solve. The story is still the same. So the only thing that you learn in this chapter is how to find the direction and magnitude of friction force. And you will see why friction has a separate chapter for itself. It is kind of messed up. So A2, how will you get? Get A1 from here and substitute in this, na God. Take A1 and substitute in this equation. Then you'll get A2 from here. Clear? Yeah. So let's see. So what's friction? When two surfaces are in contact, there is an opposition to the relative motion between them. There is an opposition to the relative motion between the surfaces. This property is called friction. Now there is one important word in this thing, two words actually, relative motion. Understand the meaning of this. Friction has no problem with motion. Getting it? Friction has no problem if you're moving. Friction has a problem when there is a relative motion. Meaning, it's like, there's an important statement here. It's like you're not feeling bad because you scored less in the exam. You're feeling bad because your friend has scored more than you. Right? Happens a lot. So friction, right? It does not oppose motion. It can oppose motion, but that's not its main goal. Let me write it like this: need not oppose motion. Let me write it like this: friction can support or oppose the motion. That is better. But it always opposes relative motion. We'll see. With some examples. Tell me one thing: when you're walking, what is the direction of friction?
Forward.
Let's say you're walking straight. What is the direction of friction? Now, see, the general thing is like, friction opposes motion. Na? So if I'm going forward, the friction will be backward. Fair enough. So if you think friction is backward, then let me ask you this: who is making you go forward? We saw from Newton's first law, right? In order for a body to move, there should be a force. So who is making you walk? There is nothing called muscle force, leg force, body force, brain force. There's nothing like that. We have seen this in the beginning. There are only four fundamental forces. The problem is, like I said, people blindly, right, when they think about friction, they always think of one thing. Friction opposes motion. So that is a problem here. Listen to this thing. Check how, when you're walking, observe how your leg moves. So when you're taking your leg and when you're striking it on the ground, look at the bottommost point in contact. So when you're trying to move your leg, you're swinging your leg backward, isn't it? The leg is swinging backward. If your leg is swinging backward, that means this point here on the ground is actually trying to go backward. If that point is trying to go backward, now look at this thing. The ground is not moving, which is at rest, but that point is trying to go backward. So friction will act forward. Is that making sense? The heel, this is what actually happens, if there is an oil on the floor and when you try to walk, this is the reason you slip. Your leg will slip backward because there's no one to stop you going forward. So here the heel is trying to slide backward. Next time, observe your sandals or your shoes. The back part of the shoe becomes thin. Ever observed it? If you look at your shoe ka sole, right? If you see the back part has become pretty thin, the front part is still thick, but the back part is becoming thin. That's because every time you hit that, that part is trying to slide backward. So here the heel is trying to slide backward. So to stop that, the friction will come in the forward direction. So the reason you're able to walk because there is a friction on the floor. If there is no friction, you can't walk. So here this friction is responsible for you to walk. So this is the meaning of, it supports motion. Like I said, friction ka job is not to oppose you. It is only one thing. It will try to oppose relative motion. Friction is responsible for motion here. Is this making sense, everyone? So same thing, tell me, when you're going on a cycle, can you tell me the direction of friction on the back wheel and the front wheel? When you're driving a cycle, right, what is the direction of friction on the back wheel and the front wheel? Options will be forward, forward, backward, backward, forward, backward, backward, forward. So four options hoga. If it was a question. A regular cycle, okay? Let's not bring some super cycle or something new one. A regular old school cycle. What is the direction of friction on the back wheel and the front wheel? Nahi Aditi. Right, Samyak. What do you guys think? Again, you need to go back to the working of a cycle. Did you ever play like this? Take your cycle, lift the back wheel, then take the pedal and rotate it fast, and then leave the cycle. Did you ever do that? You guys never did that. You guys all are so good people, right? Difficult to learn physics like that. You need to do some crazy stuff sometimes. Never did that. If you do that, observe what happens. The cycle just goes off. If you ever done that. If you're not done that, check it out. Put your cycle on stand, lift the back wheel, then with your hand or something, just drive the pedal pretty fast. So the back wheel is just rotating faster and faster. And then just leave it on the floor. The moment the wheel touches the ground, it just goes off front. So the reason for that, if you look at your cycle,
Sir, what you explained, I've done that multiple times.
yeah. So if you look at the cycle here, right? So this is the pedal here, right? So don't worry about it. So it's just a cycle there. So now when you're rotating the cycle, what are you exactly doing? You are rotating the back wheel. So while you're pedaling, you're actually transmitting power to the the back wheel. When we pedal, we are trying to rotate the back wheel. So if you look at the back wheel ka situation, the back wheel is trying to rotate. So this point is actually trying to go backward. So that point is trying to skid. It is trying to skid backward. Remember, it is always the surfaces in contact. When I say man is walking, I don't care how you are walking. I'm more interested in how is your feet on the ground. We are always interested in the surfaces in contact. This point tries to go backward. And friction doesn't like this. So friction will come forward. So on the back wheel, the friction is forward. Now, if you look at the front wheel is another problem. Front wheel has no engine or anything. The front wheel is actually being pushed by these rods. These rods are pushing forward. So the front wheel ka point is actually trying to drag forward. Because there is no, you're not giving any power to it. So on the front wheel, the friction will be backward. The front wheel is being pushed by the back wheel ka force. Let me give you another analogy here. Think of like this. Let's say, your friend is there or you are trying to push him. Let's say you're planning to go somewhere and your friend is not ready to go. So how will you push him? So your friend will be standing like this, is like, I don't want to go. And you are pushing your friend like this, Arey, let's go. Can you tell me how will the friction be on the person in the front and the person in the back? Since you're pushing your friend and he doesn't want to go, the friction on your friend will be backward. Since you're pushing your friend forward, right, your legs will try to slip backward. So on you, the friction will be forward. So if I take this person A and person B, isn't how the frictions will be there? A is pushing B forward. Is that analogy making sense? So here, A is acting like your back wheel, which is trying to move the whole cycle. Because B does not have any power, it is just being skidding. So this will be the front wheel. Now there will be few cycles there where you must have noticed there is a chain to the front wheel also. So in that case, both the frictions will be forward. Ever heard about this thing in cars, two-wheel drives and four-wheel drive? Did you guys ever hear the term four-wheel drive?
Yes, sir. Like Thar में 4x4 भी लगा था.
So if you look at a vehicle, right, especially these military vehicles and all this stuff, they are four-wheel drives. The thing is, the regular car which you use in your house, it is actually a two-wheel drive. Matlab, the car has the two wheels backward. The engine, whatever is there, that is only providing power for the back wheels. The front wheels have no power. That is the reason. Did you ever observe in movies or something? Must have seen, right? When the wheel gets stuck in the mud, no matter how much you switch it on, only the back wheel is rotating. The front wheels don't move only. Getting it? So the front wheels don't have a power. Now the problem is military vehicles, right? So these things are little unstable, but on regular roads it is okay. Because if you try to put a power transmission for the front wheels and back wheels, it becomes very expensive. But for military vehicles, right, these things travel on roads where there is no road. They have to travel in mountain areas. You need more stability and power. So the engine is connected to all the four wheels. So here, all the four wheels will have friction forward. They're expensive, but they're more stable and more reliable. By chance, even if the back wheel ka engine or shaft goes off, you can use the front wheels to run the vehicle. So next time you heard this, so four-wheel drive and two-wheel drive. So your cycle is one-wheel drive. Only one wheel is actually trying to push forward. Is this clear, everyone? Is this making sense? What is the friction trying to do? I'm just trying to give you more examples. Then let me show you something. Look at this thing. This is from a movie. The print is not good.
1000-1500 फ्लैट तो बन ही जाएंगे। वो तो ठीक है, लेकिन इंस्पेक्टर यशवर्धन
I don't know whether you have seen this movie called Force. Anyway, you know the regular story, right? Here, police is there, villains are there, they're fighting, blah blah blah, and everything. So there is something I want to show you there. So they have a fight. As usual, hero tries to show off the fighting and then his body. Look at this scene, huh? These people are trying to run away in the car. There. Look at that wheel there. And did you see how the wheel is rotating? When the car started, the front wheels didn't move, only the back wheel is rotating. So how do you stop a car from moving? One, you can apply enough force to stop the car, or you can do even something better. This guy does that. See. You lift the car. Did you see what happened? When you lift the car, the wheels are not in contact with the ground. No matter how much the wheel rotates, the car will never move. So how to stop a car? Make a body like, forgot his name, Ray, but whatever is that hero guy, and then try to lift the car. See, no matter how much you rotate, the back wheels are just rotating. There, you can see the wheels how they're rotating. And now what happens if you leave the car? John Abraham, right? Now see, if he leaves the car, it goes off. So you can try this not with your car, but you can try with the cycle. It works. So you can see there what is happening. So that is one way to stop a vehicle. If they're trying to run away, if you can lift the back wheels, there'll be no power transmission. There'll be no friction. The car will not move. So when someone says, "No, why is the car moving?" Engine force, right? Petrol force. So there's nothing like that. The reason the car moves is because of friction on the ground. Is that clear, everyone? So that's what I was trying to tell you. So the cars have only power in the back wheel. That's a two-wheel drive. So when he lifted the back wheels, no matter how much the wheel was rotating, there was no friction there. Okay, take a small break. Come back in 5 minutes. We'll continue from here. Come back in 5 minutes. So, any doubt so far? Chalo, come back in 5 minutes then. Yeah, let's start off. So why do we get friction? There are two reasons for friction. Cams on everyone. So they are the two acceptable, so far theories that we have. One is interlocking. Second is cold welding. So what is this interlocking? So when you say two surfaces are, when you say surface is smooth, even though it looks smooth from a macro level, when you actually go to a micro level and see the molecules, it's pretty zigzagged. Cams on everyone. So at a molecular level, the surfaces are interlocked. So if you actually see surfaces, there's something like this. So what happens, right? The surfaces get interlocked with each other. So whenever you're trying to move the surfaces, you have to, break this locking and then move. So this is one of the theory that was in place. The other thing is cold welding. Look at the word cold welding. Welding is normally what? You use heat to melt the things and make them stick together. But what happens, right, with surfaces, if you apply really high pressure, when you say again two surfaces in contact, in reality, even though you're saying two surfaces are touching each other, very few points are actually in contact. It's like your entire weight is falling only on these 2 points. This leads to high pressure at these points. When two surfaces are in contact, few points are touching each other. Just look at your hand. If you make both the hands, touching each other, and if you look at that, you will see there are a lot of gaps between them, isn't it? Every part of your hand is not touching the other one. You will find there are a lot of gaps in between. So few points are interacting. So this comes to approximately 1 in 10,000. So for every 10,000 molecules on the surface, only one molecule is actually interacting with the molecule on the other side. But because of this, you get a pretty high pressure and these points. It's like you standing on your toes. If you stand on your toes, you put a lot of, you're putting your entire weight on just the toe there. This leads to high pressure at these points. Which creates bonds. This phenomena is called cold welding. So basically you're sticking the two materials without applying any heat or anything. So these are called cold welding joints. So whenever you try to move the two surfaces, you need to break these bonds, and this will lead to friction basically. So at a molecular level, this is the reason why you're getting friction. Clear with this. Next thing. So let's say we have two blocks of same mass. So let's say there's a surface like this. Now, if you look at here, there is like 1, 2, 3. So there are 3 bonds. So we are keeping this on a smaller area. Let's say we have a bigger block, same mass. Now you have more bonds. So this is a larger area. So because there's a larger area, you're putting entire weight on more points. So this will create lower pressure. Because of the lower pressure, we will get weaker bonds. So the cold welding joints will be a little weaker, but there are more number of bonds. Here you're putting all the weight on small, less number of points. So this leads to high pressure. So you get a stronger bonds. So it doesn't matter how much is your surface area. Friction is independent of surface area. So if you take two blocks, same mass, same type of the surface, right? But one has a bigger area and one has a smaller area, right? The friction remains same. So friction only depends on the nature of the surface, not how much surface is in contact. Because generally it gives you a feeling like, if you have more surface, there should be more friction. That's not how it works. Again, we are taking all ideal cases. Second thing, what happens if you polish a surface? If you take a surface and if you start polishing it, what happens to the friction? Something interesting happens. So if you take friction force and if you try to increase, polish it. So friction versus polishing or smoothness. So initially friction drops and then it rapidly increases. So if you make the surfaces really smooth, stronger bonds will resist more, but the number of bonds are less narrow. Yeah. The total strength remains same. You can think of like that. You have less bonds, but they're more stronger. You have more bonds, but they're weaker. So overall, it gets compensated. So what happens with polishing? When a surface is polished, initially friction decreases because of interlocking will decrease. But if you continue to, make it more and more smooth, now you're bringing more and more bonds into the picture. Again, remember, whenever you're polishing the surfaces, you're changing the nature of the surface. It is not the same surface anymore. The surface has become more polished, so there will be more bonds and more surfaces in contact. If polished further, cold welding increases. So in this previous example, right, we are assuming the surfaces of same type. But if you start polishing this, surfaces are not same anymore. You're talking about two different surfaces, then you can't compare. If polish further, cold bending increases and therefore friction increases. So that means in NLM chapter, right, we are using the word smooth surface. Now it's actually a wrong statement. Smooth surfaces have very high friction. I'm supposed to say frictionless surface, but we will just use the word smooth. But in reality, if you take two smooth surfaces and make them touch each other, they will have very high friction. Clear with this? So that means, if you can actually can you imagine how will a perfectly smooth surface look like? How do you think a perfectly smooth surface looks like? Think of like this. Most people, right, imagine like this thing, a flat surface, like there is no bump and everything. It doesn't look like that. A perfectly flat surface, right, looks like this thing. Imagine a box of laddus. Ever seen that? When in the box of laddus, placed neatly in an order. So each laddu is one molecule. All the molecules are placed in a lattice. That is how a flat surface looks like. Now, when you take two perfectly smooth surfaces in vacuum, and if you put one on top of another, each molecule will form a bond with the other, and they'll automatically join and become one block. They'll just become one block, automatically they'll attach. You don't see this in real life is because when you take a very smooth surface, the air molecules get trapped. You start getting some rust and all these things. So when you make them two surfaces touch each other, they don't stick. But if you take two perfectly smooth surfaces of same material, put them in vacuum and bring them together, they will stick and become one block. Is that making sense? So it's called vacuum welding. There is things that also. But anyways. So remember this word. When you say smooth surfaces, they actually have very high friction. We should use the word frictionless surface. But okay, anytime you hear the word smooth, understand it as they should polish less. You should not polish too much actually. So polishing up to an extent is good. More than that, it goes bad. We should say frictionless surface. Anyway, so that is a little bit of introduction about friction. So we know there is a friction. We know why it is coming in the first place. At a molecular level, what is happening. Now coming to the main thing, like I said, there are two things that we need to do. We need to find the direction and we need to find the magnitude. So first one, let's find the direction of friction. Finding the direction of friction. Remember, friction has only one purpose in life, to oppose the relative motion, right? What do you mean by that? Just to give you an example, think of like this. Let's say we have your friends A and B. You're in the middle. Listen to this thing. Your job is simple. Your job is to make sure A and B are together with you. Clear? That's your only job in life. A and B should be together with you. Now imagine B starts running with 10 meters per second. What can you do to keep them together? What can you do to keep them together? You can completely stop B, option one, or forget about B, make A also run with 10 meters per second. You're getting it? My job is not to stop you. My job is to keep you together. So I can just forget about B and make A also run with 10, or make A run with 5 meters per second and decrease B ka speed to 5 meters per second. I have three options. I can stop B, or forget about B and make A move, or decrease the speed of A and increase the speed of A and decrease the speed of B. Is that making sense? Among the three options, friction will prefer the third option because when I try to stop A, I get a force. Newton's third law, I have to use this force somewhere else. I'll use that on A. So that is what friction does every time. So first step, So whenever you want to find the direction of friction, assume the surfaces are frictionless. You start with an assumption. Step 2, then if the friction surfaces are frictionless, see the tendency of the bodies to move. Means if there was no friction, how will these bodies would have moved? See the tendencies of the surfaces to move. Third, then apply friction in such a way to oppose relative motion. One trick I can tell you to get the force cut directions, imagine like this. Whenever you say two blocks are touching each other, imagine both are connected by small springs. So imagine this cold welding bond similar to springs. Now it will be easy to figure out the directions. Now let's see some cases. Case 1. Let's say we have two blocks, A and B. Let's say A is going with 2 meter per second. B is going with 3 meter per second. Now imagine you are the friction, right? A is going with 2 and B is going with 3, and you're not happy with this. What are you supposed to do? Decrease B and increase A, isn't it? Your job is to keep them together. So think of like this. If they both are connected by springs, the picture would look like this. The springs would become like this. So what will the springs do? These springs will pull A forward and the same springs will pull B backward. Does that make sense? If A is going slower and B is going faster, the springs will stretch like this. So your job as a friction is to make sure A and B are going together. So stop the guy who is going faster and increase the guy who is going slower. So you're supporting A ka motion and you're opposing B ka motion. Case 2, let's say this is going with 1 meter per second and this is going with 2 meter per second. What will be the direction here? What is the direction of A and B now? Try. I'll give 10-15 seconds. It's not tough. Same story. A is trying to go to the right and B is trying to go to the left. So you as a friction, you want to keep them together. So if this were springs, you can imagine like this. The springs would have become like this sort. The springs will stretch this sort. So these springs will pull backward and these springs will pull forward, isn't it? If both of your friends are running in opposite direction, you catch both of them and pull them inside, isn't it? So in this case, friction opposes both of them. It is not supporting anyone. Here, friction will be 0. Why? There is no relative velocity. Like I said, friction does not have a problem with velocity. If both are going together, the springs will never stretch, so there'll be no force. Any doubts on case 1 to 3? All clear with these 3 cases? Siddesh, Priyansh, Claudia, clear with this? Tanishka, Yashvi? Case 4. What if block A ka speed is 5 meter per second? Acceleration of A is 1 meter per second square. Block B ka speed is 5 meter per second. Acceleration of B is 3 meter per second square. Now what about the direction? What if you have accelerations also? Again, how we got the acceleration, don't worry about that. Assume you have this. Let's get the directions, everyone. So case 4, at that instant it will be 0, but if you give little time, we can clearly see B has more acceleration, so B will go faster. So even if I give a very small time delta t, VB becomes greater than VA. So friction will act backward on B and it will start supporting A. Clear with this?
Sir, can you explain this again?
What about case 5? What happens here? So case 5, see what happens. Initially, if you see, B ka speed is more, but A ka acceleration is more. So there will be one time when VA becomes equal to VB. So U plus AT, so this will be 4 plus 2T is equal to 10 plus T. So from here we get T is equal to 6 seconds. So for T less than 6 seconds, VB is greater than VA. So A goes faster than B. So friction will oppose B and support A. For T greater than 6, speed of A becomes greater than B. This is the thing about the friction. Friction doesn't care about the blocks and everything. It'll have only one purpose in life. Who is trying to go faster? A is going faster. I'll oppose him and I'll support B. So if you see in the middle of the problem, the friction has changed direction. We have never encountered a force like this so far, which changes in the middle of the problem. If mg is down, it is always down. Tension is up, it is always up. Friction doesn't care about all that stuff. If the velocities change, I will change my direction. Is this making sense? This is the reason why this force was it's like kind of like a rogue. It doesn't follow any norms or anything. It has only one purpose in life. My job is to make sure the relative velocity is decreasing. Is case 5 clear, everyone? So the friction will change its direction after 6 seconds. The FBD itself will change. Clear, Arya? Arya? Arya, are you there? Okay. Adjust your camera a bit, right? Let's see one more case. I think if you got this, then I think you understood how to get the directions. There are 4 blocks. All surfaces are rough. Ground is also rough. Get me the direction of frictions on A, B, C, D. Right. I'll give you a minute. There are 4 bodies there. So how do we handle this? I'll just give you an idea. See, the friction between A and B. See, friction between A and B has only one purpose in life. I want to make sure A and B are together. I don't care what happens to the other surfaces. So when you talk about A and B ka friction, don't worry about the other blocks. So it will be one of the 5 cases that we have done. So when you study for A and B, look at only those 2 surfaces. Don't care about B and C. When you see for B and C, don't care about other surfaces and so on. So if you look at A and B, this is your case 1. A is going faster than B. So this friction will oppose A and will support B. B and C both are going opposite to each other. Friction is not happy with that. So it will oppose B. It will also oppose C. Between C and D, C is going faster than D. So this will oppose friction and this friction will support D. But the ground is not moving and D is going forward. This will be F ground. Please check the directions of frictions, everyone. Every surface will think only about its own 2 blocks. It doesn't care about what other blocks are doing. All clear with the directions. Yeah, great. So there, now you know how to find the directions. That's the first part. Second thing, finding the magnitude. This is completely experimental. So the reason why we have a separate chapter for this thing is this friction is such a type of force which can change its direction anytime it wants. It has no fixed rules. It has only one rule. Relative velocity is there, it changes direction. Finding magnitude of friction. So let's see this. So again, what is the experiment? So we take a block of mass m, put it on a rough floor. The other side, you attach a pulley with a bucket or something. And what you do to the bucket, you keep pouring sand inside. So this side is rough. You start adding sand inside it. Sand or anything, variable mass basically. So here we'll get the weight mg. Remember, this is a variable. As you keep changing the mass of the sand, the mass is changing. This force will be tension. This will be tension. So if the string is pulling to the right, I know friction should act on the backward to keep it at rest. There is a normal reaction. This is the mg. These are all the forces on the block. Now, as you keep adding more and more and more sand, we'll notice something. This is what we observe. As m, basically the sand increases, we notice nothing happens. The block remains at rest. Again, remember, this is an observation. Then suddenly, right? So initially what was having block remains at rest. So we know T is equal to mg. And we also know T is equal to friction because the block is not moving. That means F is equal to mg. And you're saying M is changing. That means you'll observe friction is increasing. This is the second problem that we have. This friction curve magnitude is also not constant. Depending on the situation, it can take whatever value it wants. If you put less sand, I'll get less friction. If you put more sand, I'll get more friction. So that is friction increases, right? And then we observe friction is increasing initially. Then something happens. Then after a certain value, suddenly the block accelerates. Block accelerates with a jerk, meaning it doesn't, start gently. It just feels like, violently it starts moving. Like it feels as if, think of like this. Did you ever play with your friend or sister or someone? You catch their hand and they want to run away. They're pulling, but you're not leaving. They're pulling, you're not leaving. They're pulling, you're not leaving. Then you suddenly leave it. Ever done that? They fly away like that. So this thing, something, it behaves like that. The friction is not letting you go, not letting you in, then suddenly it just leaves and the block just flies off. Something of that sort. It doesn't fly off, it moves off. So if you try to plot this graph, this is what we notice. So measuring all these values in the experiment, and when you plot the value of friction versus the mass of the sand, this is the graph we get. The graph increases linearly, and then at some point it just drops and then becomes constant. Now we need to see why it drops and why it becomes constant. So if I name these points, let's call this thing O, let this be A, let this be B, and gone. So this is the scenario. So from O to A, right, the block does not move. Does not have any relative motion. That is fine. So friction is increasing gradually. And once you reach at point A, we have maximum friction. So friction will increase till here and then it would suddenly drop. So this point, right, is called as static friction. Look at the word static. Matlab, there is no relative motion there. Surfaces are not moving. This friction is called static friction. And if you look at this peak value here, this is called F static max. Meaning the surface is still not slipping and you have reached a maximum value. So F static indicates there is no slipping. So from O to A, the friction, there is no slipping and you're having a friction. It's a static friction. Now on A to B, something happens. In AB, the friction drops. Now, why does that happen? Think of like this. Imagine you are there and let's say I'm trying to run away. Tell me in which case it is more easy, or in which case are you applying more force? Let's say if I'm standing here and you're catching me, right? Case two, I'm running with speed V and then you're trying to catch me. In which case, can you catch me more strongly? If I'm standing beside you, you are catching me. In case two, I'm trying to run and then you're trying to catch me. In which case it is you can apply more force on me. In which case you'll have a better grip on me. When I'm standing, right? Isn't it? Think about it. Let's say if there is a pole here and if you're falling from a building, is it easy to catch the pole while falling down? Or is it easy to catch the pole, with some strength when you're at rest? So something similar happens here. So the moment the friction reaches maximum and the blocks try to move, so when the surface moves, you are breaking all the bonds. That's where the surface moves. The bonds are broken. And they're trying to find a new bond. So it's trying to find a bond with the other molecule in the front. But the problem, now you started moving, so you're not giving enough time. Every time the bond forms, you're breaking it immediately. So these bonds don't form properly. They do not have enough time to form the bonds completely. You get kind of like an incomplete bond. So when I'm standing, you're catching my hand very tightly. Let's say you can apply 100 newtons. When I'm trying to run and then you're trying to catch me because my hand slips or something, maybe you're applying only 70 newtons. This leads to weaker bonds and the friction decreases. Did you ever see this thing, this Guinness World Records ka competitions? So there's a person there, he's pulling an aeroplane. Ever seen this kind of records? Some person is pulling, railway car train. So if you observe that person, right, initially when he's trying to pull, he's applying a lot of force, lot of force, lot of force. But the moment that plane or that train moves a bit, it becomes very easy. He starts running. The amount of effort this guy kept in order to move it, once it moves, it kind of becomes easy to move from that point of time. Is that making sense? So this is what was happening. Once you break the bonds, right? And if it is continuously moving, the bonds are continuously breaking, forming. You're not giving any time to form properly. But let's say you stop the block for a millisecond, the bonds will suddenly start forming and it becomes again maximum. So that is the reason what happens in B. And after B, the block moves with a constant friction. So you will settle down at a little lower value because the grip is weaker. So that is the reason why you have a dip in the friction. Because once you start moving, the molecules cannot get proper grip on each other. The bonds that form will be a little weaker. So as long as you're moving, the bonds which are forming are continuously weaker. Clear, everyone? That is the theory, what is happening there. And then again, from all these experiments, when you try to figure out the value, what these people found out, that maximum value that we have, you can find the peak value from a graph. So this F static maximum value is proportional to the normal reaction. So this F static maximum value is given by mu static into N, the proportionality constant. Be careful. F bar is not equal to mu S into N bar. The directions are, and they're not parallel vectors. We are only comparing the magnitudes. Look at this, friction is there and N is this thing. F and N are perpendicular. You can't compare two perpendicular vectors, they're not equal. F bar is not equal to mu S N bar. Mod F is equal to mu mod N. So this constant mu S is called coefficient of static friction. So there, so we got a friction which can change its magnitude. We have a friction which can change its direction. It's messed up force. So there, so if I put down the main formulas there, Fs maximum is mu S N. I'll give an example what it means. If I simply write F static, mean not maximum value, F static must be always less than or equal to Fs maximum. So if someone asks you what is friction, don't say mu into n. It is always mu s into n. That is the most important thing. F kinetic, that means once the block starts moving, the friction becomes kinetic. So kinetic matlab it is in motion. So F kinetic will be mu k n. This is again becomes constant. Mu s is greater than mu k. Like I said, while you're moving, the bonds are weaker, so the friction will be little less. These are your main results, everyone. So if someone asks you what is friction, don't say mu s into n. It is less than equal to mu s into n. I'll tell you what it means. So from this, we also define a word called contact force. Contact force is nothing but the force due to being in contact, which is normal reaction and friction together. Sometimes in the exam, they'll ask you find contact force. They're not asking you normal reaction. He's asking you to friction and normal reaction. There, now we know how to find the magnitude, partially, kind of, and we know how to find the direction. Now we know everything about the friction. Be careful with the word contact force. Huh? I still remember when I wrote the JEE exam, they gave contact forces 40 newtons. I took N is 40. I solved the entire problem. And in the question, they said G is 9.8. I took G as 10. I got answer 3.6. It was an integer question, so I marked 4. It was right. My friends also took N is 40. They took G 9.8. They got 3.4. They marked 3. They got wrong. So I did 2 mistakes and luckily I got the right answer. But contact force is not the normal reaction. Clear with this? So let me show you with an example what this means. So listen to this example. Let's say we have a block here of 5 kg. And let's say friction mu is 0.5. And let's say someone is applying 5 newtons. What will be the friction on the block? Now see, blindly if you write Fs max is equal to mu s into n. Mu s is 0.5, n is 50. This will be 25 newtons. This is the maximum value of friction. Now you think about it. If I apply 25 newtons backward and you're applying F is equal to 5, won't the block go backward? Means if I push you forward, you're going backward. There is a ghost in the house. That is number one. Second thing, as a friction, what was your job in the first place? Your job was to keep the block and the ground together. And what are you doing now? You're applying 25 and you are only moving the block. Are you getting the problem here? Again, I'm saying friction ka job is not to apply 25 newtons. Friction ka job is what? Friction says, I want to keep them together. So someone is applying 5, right? If I can apply 5 newtons, I can keep it at rest. So why will I give 25? We need only 5 newtons to stop the relative motion. I can give you 25, but I need only 5 to stop you. So I'll give you 5 and my job is done. Are you getting this? Meaning, think of like this. If I apply 25 newtons, the springs will break, the cold welding will break. But up to 5, I can stop the relative motion. So friction is not 25 newtons here. This is what I was saying. Friction can be any value less than or equal to 25. Depending on the situation, friction will change. Suppose if I apply F is equal to 10 newtons, then what do you think will happen? Then friction will be 10. If I apply friction is equal to 23 newtons, then friction will be 23. You're getting the friction will keep changing its value. If I exceed 25, then friction will come maximum. Meaning if I give an analogy, think of like this. So listen to this analogy. Let's say you have 1 lakh rupees and you're ready to give it to me. Okay, you have 1 lakh rupees and you're ready to give it to me. I'm asking you for 20,000. How much will you give? 20,000, right? But you got 1 lakh, no? Okay. I ask you 50,000. How much will you give? 50, right? But you have 1 lakh, right? If I ask you 2 lakhs, you will say, sir, maximum I can give 1 lakh. Take this. I can't give more than this. Are you getting it? Just because you can give 1 lakh doesn't mean you'll give me always 1 lakh. If I ask you for 20,000, you'll give only 20,000. If I ask you 50, you'll give me 50. If I ask you for 2 lakhs, that is when you will say, I can give you everything that I have maximum, but done. I can't give you more than that. Are you getting this? Just like friction. Friction is saying I can give you 25. Doesn't mean I need to give you 25. You're asking only for 5. So I'll give you 5. Ask for 10, I'll give you 10. Ask for 23, I'll give you 23. You ask for 40, then I will say, boss, I can give you only 25. Take this, right? I can't give you more than this. Is this making sense? Friction gives only how much ever is required. It doesn't give maximum every time. Clear with this? There. Now you know how to find the direction. Again, we will see problems. That is when it gets more clear. But I hope you got a rough idea there. So there is no specific formula for friction. If someone asks you what is friction, don't say 25. You need to check. So we know how to find the direction. We know how to find the friction. So that's a bit of a theory about friction. Technically, that is the entire theory of friction, what we did today. So next class, when we catch up, we'll continue from here. So make sure to go through the theory before the next class. So we will do different problems, right? We will take up different variations and all. Like I said, it looks like NLM only. There is not much of a difference once you know the direction and the magnitude. But yeah, direction and magnitude, that itself is a pain. Okay, with that, we'll wrap up for that day, right? So do make sure to go to the NLM notes first. We did almost 54 questions there, so revise that. And friction, we will continue again from Tuesday. Okay, there was a test online. Hope everyone has given it. In case you have not given, it is online till 11:30. So make sure to give.